Now let's consider an application of this Green's theorem. Okay, so here's the first example. So we have a closed curve that is defined in the plane, and our closed curve C contains three paths, the union of three paths C1, C2 and C3. The path C1 is a part of a parabola y equals x squared, and then it's going to connect to the line y equals 1, and then the end curve is x equals 0, this vertical line. Now if you consider the union of these three curves, you will get a closed curve. Now in this problem, our goal is to evaluate this line integral f dot ds, where C is the union of these three curves and f is this vector field. Now if you want to evaluate this line integral using the technique that we developed in chapter 13.2, we have to evaluate three different line integrals. But what we can do is we can apply the Green's theorem, because here we have a closed curve, therefore we have a domain bounded by those three curves. So instead of evaluating this line integral, what we could do is we could evaluate a double integral over this domain D, and the double integral is given by this quantity. Okay, so let's do this. So line integral over the closed curve f dot ds, this equals to double integral over the domain D. Now what is your integrand? Your integrand should be, so if this is your P and if this is your Q, should be partial Q over partial X minus partial P over partial Y dA. Actually, this is why we learned double integrals in chapter 12. Okay, so let's evaluate these two partial derivatives. Okay, the first component contains the derivative of q with respect to the x variable, and your q is this 2 times x squared y minus y squared sine y minus second part contains the derivative of p with respect to the y variable, so x plus xy squared dA. Okay, now with respect to the x variable, this term y squared sine y is a constant, and then here we have 2 times x squared y, so derivative of that one with respect to the x variable should be 4xy plus 4xy, then derivative of the second part is 0 minus, now derivative of this one with respect to the y variable should be 2xy, 2xy dA. Again, derivative of this first part is 0, because derivative of x with respect to the y is 0, and we have to treat x as a constant, and then we have x times derivative of y squared is 2y. Now if you simplify the integrand, you will get 2xy dA. Now what is dA? dA is an area element on the xy plane. So if this is your dA, that's your dA. Okay, let's see. So I think we should consider 2xy dy dx. Okay, let's do that. Now my first variable of integration is y. So now the lower limit of y is given by the parabola x squared. Upper limit of y is given by the horizontal line y equals 1. And then x goes from, x should go from 0 to 1. Yes. X goes from 0 to 1. Okay, now let's evaluate this integral. Zero to 1, we can pull out 2x from the inner integral because my first variable of integration is y. And if you integrate y with respect to the x variable, you will, with respect to the y variable, you will get y squared over 2. Lower limit is x squared, upper limit is 1 dx times 2x from 0 to 1. Two x times, apply the upper limit first, get 1/2 minus square of x squared over 2 dx. Now if you simplify this, you will get 1 minus x to the power 4 times x. That's your new integrand. You can cancel this 2 with this 2. You'll get that. Now let's distribute this x. You have x minus x to the power 5. Okay, now we have an integral of a difference which equals to the difference of the integrals. If you integrate x, you will get x squared over 2 minus integral of x to the power 5 is x to the power 6 over 6. Apply the upper limit first. We get 1/2 minus the lower limit is 0. And if you substitute 0 for x, you will get 0 minus, now we have 1/6 minus 0. And so basically we have 1/2 minus 1/6. This equals to 1/2 is the same as 3 over 6. 3 over 6 minus 1/6. This is 2 over 6, which equals to 1/3. So here we used Green's theorem to evaluate the line integral over a closed curve.